Hello. Now we have been discussing the gyroscopic effect, and in the last sessions we have understood what is gyroscopic effect and how does it affects a mechanical system when in a dynamic situation. Now in this session, today's session, we will discuss about the effect of gyroscopic couple on the stability of floating vessels, or I'll directly mention it as the sea vessels, or you can say the ships or boats which are having motors to run them. Now how exactly this is going to affect the stability of a ship or a floating vessel. Now if we see the structure or arrangement of a ship or a floating vessel, so they are run by motors or turbines, usually the shaft being parallel to the lateral axis of the ship. Now what happens is, when a ship steers, that means at that time the axis of the spin, the rotor, that is getting turned. So we have seen that when the axis of spin is rotated about a perpendicular axis, then about the third mutually perpendicular axis there is introduction of a couple which is called as a gyroscopic couple. Right. Now before we move on to see the various conditions for which we will be working out the stability of a floating vessel, first let us get acquainted with certain terminologies which are used in case of the floating vessels. So the front side is called as, or the front of a ship is called as a fore. It is also termed as a bow, and the rear side is called as the aft, or it is also called as the stern. Right? Then, now this is the elevation which I am showing. So if you see this ship or a boat in the top view, so maybe it is, so this is the axis, so from the top view if I see, so this is the bow, front end is the bow and the rear end is the stern. Now the left side, so I have a ship or a boat for you. So all of you know we have been making this boat. So if I place it this way, right, so the front is the bow, the rear is the stern. So when I am looking at it from the top, so my left or the left side, so we are facing in the direction of the motion of the boat. So when we are facing the front, so the left side is called as the port side and the right side is called as the starboard. So these are the terminologies which are used when we are dealing with the ships. Now, how or in what conditions this stability is getting affected? There are three conditions basically. So first, while steering, this is the first condition when floating vessels get affected, which is steering. Steering means when the boat is moving, so either it will steer to the left or when it is steering to the right. So that means now compared to this boat, if I say this is the axis of the rotor of the boat, so when it is say turning to the left, that means the rotor axis is turning to the left. So we see that as if the spin axis is turning, or when it is turning to the right. So this condition is called as steering. So that means on the surface of the water, either it is turning to the right or to the left. Second condition when it is getting affected, it is the pitching condition. When the ship is pitching or the vessel is pitching. Now what is pitching condition? Now when the ship is moving, now if it is a rough sea, so the waves will be coming. So when the waves will be coming, then the ship will be moving over the waves. So the bow is getting raised and then it is falling down. So this motion of the ship is called as the pitching motion. That means if this is the rotor blade, the rotor blades are turning this way. Now both these conditions will take into the condition of the forced precision conditions. So a gyroscopic couple will be acting. So we will see how it is affecting. So second condition is called as the pitching, and the third condition, though there is no as such effect into the stability due to gyroscopic effect, but the third condition of any floating vessel or a ship is the rolling condition. Now what is the rolling condition? So we have seen steering, that is turning to the left or to the right. Then we have seen pitching, when the bow is raising and falling down. And third condition, when the boat or the ship is turning about its lateral axis. So this condition is called as rolling. But if you see, as such, there will be no effect of the gyroscopic couple during the rolling. But definitely during steering and the pitching condition, there will be the stability is definitely affected due to these conditions. So first, if we see how or what will be the magnitude of the gyroscopic couple. Now let us take this condition as the rotor axis is parallel to the lateral axis of the ship. It is definitely or certainly the axis of the rotor blades will be, or the rotor or the prime mover of a ship or a vessel will be always parallel to the lateral axis. Now again, when we are analyzing, we will right now place ourselves as an observer behind the ship. So we are looking at the rotor from the stern. So we are looking at the rotor from the stern. Now let us take this condition that the rotor blades are turning clockwise, right? So the rotor or the prime mover mass is rotating, or the spinning mass is rotating in the clockwise sense. And maybe let us say that the ship is turning to the right, or it is taking or steering to the right. We can even change the condition and see how the couple is getting affected, right? So the rotor mass is, let us say it is having some mass m, and it is spinning at an angular velocity omega, or maybe the RPM is known to us. So as we know, the magnitude of gyroscopic couple, so we'll say the magnitude of gyroscopic couple due to steering will be I omega p, where omega p is the precision velocity. So let us say there is a linear velocity, the ship is moving with some linear velocity v, and it is turning at a radius, let us say r. So if the linear velocity of the ship is say v, and turning radius is r, so I can say that the precision velocity, so this omega p, precision velocity is equal to v by r. So this is what will be the magnitude of the precession velocity. Omega, we know omega is the angular velocity of the spinning body, and I is mass into the radius of gyration square. So if we know all these values, so I can determine the magnitude of the gyroscopic couple due to steering, which we know as I omega p Newton meter. So this will be the magnitude. Now magnitude is done. So we have determined or understood what will be the magnitude of this gyroscopic couple acting. But now we have to understand how it is going to affect the conditions of stability during the steering. So for that I will have to understand, or I will have to determine, because if I just find out the magnitude of a couple, I will say it is a incomplete answer, because when it is a couple, then I must as well know what is the sense of application of this couple as well in the system. So to understand the couple, we will go for the vector diagram to understand this. So again, so the axis of spin is in this case we have seen that, or we have kept it as the horizontal. So this is the axis of spin, right? Now the boat is steering to the left, sorry, I have taken the condition as right. So the boat is turning to the left, right. So I am, as an observer, when I look at it from the top, it is taking a right turn. So that means the boat is turning about the y-axis. The boat is turning on the exit plane or the horizontal plane. So it is turning about the y-axis. The y-axis becomes the axis of, so this x-axis is the axis of spin. The y-axis is the axis of precession. So this is axis of precession. So the remaining third mutually perpendicular axis is the z-axis. That means as an observer, if I see, so my position should be somewhere here. So the z-axis, which is perpendicular to the board right now, will be the axis of gyrocouple. So this is axis of gyrocouple. So whether it is active or reactive, that we will see. So we have considered this to be turning clockwise when looking from the stern. So if it is so, if I apply the right hand screw rule again, so this is my right hand, it is turning clockwise, so I will turn my fingers or curl my fingers in the clockwise sense, so the thumb is pointing outwards. That means the spin vector from the pole, so if I name it as, say, pole as O, the vector will be pointed outwards. So this is spin vector. So this is the spin vector which is turning clockwise. How is the precession? Precession, we have seen that it is taking a right turn. So from the top, if I look, it is again turning clockwise. So as an observer, when I use the right hand screw rule, so when I curl my fingers, the thumb is pointing downwards. So the precession vector is pointed downwards. So this is clockwise sense. So this vector is the precession vector which is turning clockwise. So the third mutually perpendicular axis now will give me the sense of the gyroscopic couple. So how do we achieve the vector for gyroscopic couple? When we turn the spin vector in the sense of precision. Precision is clockwise. So I'll just pick the spin vector and rotate it in the direction of precision by 90 degrees, and precision is clockwise. So I turn the spin vector clockwise. So I get this vector. So I turn it in the sense of precision by 90 degrees. So I get this vector as the gyroscopic couple vector, or this is the active gyroscopic couple. So what is happening here, that means, so if we see as an observer, when I am standing here and looking at it, so the vector is pointed outwards, so that means this vector is clockwise from this as a position of observer. So it is turning clockwise, so this vector is clockwise. So this is clockwise. So how it is going to affect? See, this effect will be experienced at the bearings of this rotor. Fine. So this shaft of the spinning body is trying to turn. So it is about the y-axis, that means perpendicular to board axis. This shaft of the rotating body or spinning body or a spinning mass is trying to turn clockwise, right? So the shaft of the spinning mass is trying to turn clockwise. So the frame or the boat, this is mounted on the boat, so the boat or the bearing will react in the counterclockwise sense. So the reactive couple will be exactly opposite to the active couple. So that means we get the reactive couple to be like this. So this vector is the reactive gyro couple vector. So this is the reactive gyro couple vector which is pointed towards the observer or me. So that means this is counterclockwise. So this is counterclockwise. Now how it is affecting? So what is happening if it is counterclockwise? So when the ship or the boat is trying to turn or steering to the right, so this is experiencing an active couple which is clockwise, right? But the boat or the ship or the frame will try to, or it will react to that action of couple, and that reaction will be counterclockwise. Now what happens in case of floating vessels is, this is floating on water. So definitely, as we have seen in case of stability of four-wheelers on the road is a solid surface which gives a positive reaction to the vehicle. But here it is a fluid, so it gets very easily deformed. So in this case what happens is, the water does not give that much reaction. So what happens is, so that means the reactive is counterclockwise. So what will be happening in this case is, the bow will try to dip, right? So this is what happens. So when a ship at a considerable speed of this rotor, and when it is taking a right turn, so while taking a right turn, what is experienced is the bow of the ship dips into the water. So the if you have experienced seen somewhere the speedboats, it is very easily seen in such cases. When a speedboats are trying to take turn, the accidents happen such cases. But this is how it is going to affect. So what the condition will happen in this case, and the ship will always react. So we will be always able to see the reaction. So when it is taking a right turn, so we get the effect as when taking the right turn, the bow is dipped. So if I want to comment on the stability, what will happen when the ship is steering to the right when the given condition of the spinning mass is this. So my comment will be, when steering to the right, the bow is getting dipped. Now, if let us try to deduce the situation, if it is taking a left turn, what will happen? So if the condition is such that, or case 2 if I take, when this in the same condition, the ship is turning to the left. So when the ship is turning to the left, see, the spin vector condition is not going to change. The precession condition has changed. So now it is turning to the left. So when it is turning to the left, that means it is counterclockwise. So I get the precession vector for left turn in this fashion, which is counterclockwise. So turning to the left. So that means when how I get the couple vector, I'll have to turn the spin vector in the direction of the precession. So instead of reactive, this becomes the active couple and this becomes the reactive couple for left turn. So reactive couple becomes this. So that means for during the left turn, what is happening is the shaft of the spinning mass is trying to turn counterclockwise. So the bearings or the frame or the ship is reacting in the clockwise sense. So what is happening? So when it is taking a left turn, it is seen that the bow is raised or the stern and the aft is dipped. So we experience this situation. So that is why during this steering and all, it becomes very necessary as it is moving on water. So the bow is getting dipped, or so it makes the movement of the ship quite unstable. So now we will move on to try to understand the second condition, which is called as pitching. So now let's analyze the condition for pitching. So what is the pitching condition? As I have shown you, this is the boat. So the bow is rising and falling on the waves, right? So say this is the lateral axis, and on this plane the bow is rising and falling down. So say this is this motion of the bow on the waves, it is falling. So maybe I take this angle as the pitching angle. Right now I call this as pitching angle. Now try to understand this situation, how the forced precision is there in this situation. So the spinning mass is rotating about this x-axis or the spin axis, right? And during pitching, what is happening is this axis of spin is rotating about the perpendicular axis. That means the perpendicular axis to the board. So pitching is taking this way, right? So if this is the axis perpendicular to the board and this is the rotor axis or spinning mass axis, the pitching is taking this way. So that means this axis, which is perpendicular to the board, becomes the precession axis. Now the wave of the motion of the waves. So first let's see what will be the magnitude. So definitely when I say magnitude of gyroscopic couple during pitching, of course it will be I omega P. Now the rotor mass is m and it is spinning at angular velocity omega. Omega p is the precision velocity. Now comes the question. So precision is taking this way. So if I can determine this precision velocity, which will be about the perpendicular axis to the board, if I can determine this omega p, I can very well determine the magnitude of gyroscopic couple. Then what should be the omega p? Now of course the waves of the sea, they are natural, and this motion, so the wave motion is actually a simple harmonic motion, right? If it is so, that means the pitching, the rising and falling down of the bow of the ship is following a simple harmonic motion. So that means the displacement, this theta p, is simple harmonic. So we know what is a simple harmonic motion, right? So I can relate it to a particle rotating in a circle, and at the same time a particle is moving, for giving a sine curve. So how it is actually? So when this is turning, rotating about a fixed point, at the same time this particle is traveling the same. So this, if this is happening at time t, so this entire rotation of 2 pi, this is also happening at time t, which is called as time period. And this, if this is so, this is turning at an angular velocity of omega. So at any condition, if I say this is theta p, so this theta, what will be theta? At time t, if this is the displacement, then theta by t must be omega, or theta is equal to omega t. So the expression we know for simple harmonic motion, y is equal to a sine omega t at given time t, where a is the amplitude. But here we are talking about the angular displacement. So when we are talking about angular displacement, which is theta p, so I will say theta p is equal to theta 0, which is the amplitude, right? And theta 0 will be the maximum angular displacement from the mean. This is the amplitude, is sine. Now this omega which I mean the omega or angular velocity of particle analogous to the displacement. It is not this omega, right? So it is not angular the spin velocity. We are talking about the simple harmonic motion omega. So this as omega t. So which relates to this condition, right? So now what we are trying to find out? We are trying to find out the precision velocity. Velocity is rate of change of displacement, and this is the displacement. That means I can say the precision velocity will be equal to, right? Because this is taking at time at t. So this will be, so amplitude is constant, so 0, theta 0, omega cos omega t, right? So that means omega p is varying. Of course, it is simple harmonic motion, so the velocity is increasing, reaching to the max, becoming 0, and then coming back. So gradually again omega p is increasing, reaching to a max. So at max omega p condition only, it is going to give me the maximum magnitude of gyroscopic couple. So that will be the, so what I need to find out? I need to find out what will be omega p max. So the precision velocity maximum will be maximum only when this cos omega t value is equal to 1. The maximum value of cos is equal to 1. So that means maximum omega p will be equal to theta 0 into omega. So see, we just now I have said that theta is equal to omega t, right? Theta means any instantaneous displacement of the bow. So we get omega as theta by t, which will be equal to, for a given cycle it is 2 pi by t. I have showed you just now, the particle is rotating at omega at time t. So this omega will be 2 pi by t, where t is the time period. So omega p max is equal to theta 0, where theta 0 is the maximum amplitude, maximum angular amplitude of displacement of the bow, and this is 2 pi by t, where t is the time period of this, or periodic time or time period of the SHM motion. So when this is known to me, so I will find out omega p max. So that means I can say the magnitude of gyroscopic couple due to precession, which will be the maximum gyroscopic couple, is equal to I omega p max. So this is how we determine the magnitude of the gyroscopic couple, for pitching. So we have understood, or we have determined the gyroscopic couple magnitude. Again I will say that this is incomplete until and unless I determine the sense of application of this couple, and we will try to see how it is going to affect. So again we will go for the vector diagram or vector analysis. So the spin is not going to change. Spin axis is the x-axis. So the spin axis is the x-axis. So this is the spin axis. This is the, let us say, the pole. This is the y-axis. So this is the y-axis and this is the z-axis. Now this time our boat is, or our ship is this way, and the pitching is taking place this way. That means the z-axis is the axis of precession. So the z-axis is axis of precession. Right? And the y-axis is the axis of gyrocouple. The y-axis is the axis of gyrocouple this time. So now let us take the condition when the bow is falling down. So I take the condition here, the bow is falling. So I take the condition bow is falling. Let us try to understand what is going to happen. So when the bow is falling, so of course first let us mark the vector of spin. So spinning mass is turning clockwise, we have said. So the spinning vector is pointing outwards from the pole according to right hand screw rule. So I get this vector as the spin vector. This as the spin vector which is turning clockwise. Fine. Now let us try to understand the precession. So precession, both the ship is, we have said that the bow is falling down. So when the bow is falling down, that means the spin axis is turning counterclockwise. When the bow is falling down, as an observer from this side, it is turning counterclockwise. So if it is turning counterclockwise, then according to right hand thumb rule or the screw rule, the thumb will be pointing towards me and the fingers will be curled counterclockwise. So I get the precession vector pointed towards the observer. So what I get this? I get this as the precession vector. So how is the precession vector? Precession vector is counterclockwise. So when the precession vector is counterclockwise, now I have to determine the couple vector. So that means this y-axis in this case is the couple axis. So how do we get the couple vector? When we turn the spin vector in the direction of precession by 90 degrees. So when I turn the spin vector in the direction of the precession by 90 degrees, that means this. So when I turn, it is counterclockwise, so spin vector has to be turned in the direction of precession. So I get this vector as the active gyroscopic couple vector. So I get this as active gyro couple vector. And how it is from as an observer, when I am looking at this system from the top, I see that the vector is pointed downwards. So that means this is turning clockwise. Vector is downward, so it is turning clockwise. So how will be the reactive vector? The reactive gyrocouple vector will be pointed upwards, exactly opposite to the, so we get the reactive gyrocouple vector pointed towards the observer. So this is the reactive, so this becomes the reactive gyrocouple vector which is pointed towards the observer. So if it is pointed towards the observer, then it is counterclockwise. So it is counterclockwise. So that means what is happening is, when the bow is falling down, the shaft, spin shaft, is having a tendency to turn to the right or turn in the clockwise sense. But the bearings or the ship will react to it. That means the ship will try to turn in the counterclockwise sense. So what is happening? So when the bow is falling down, it is not falling straight. Rather, so it is supposed to fall straight, but it is not falling straight. It is falling in a counterclockwise sense. So it is not falling straight. It is falling this way. Right? So it is having a twist while falling down. So this makes it unstable. So if it is turning counterclockwise, right? So if it is counterclockwise, so that means it is trying to turn to the left. So what is the left side? It is the port side. So in this given condition, then what will be our comment as far as the stability is concerned? So in this given condition, when the bow is falling down, the ship is turning to the port side, or it is falling to the port side. So that is how we comment on the stability. The conditions we can again see the situation. We can if we change the condition while rising up, so that means in that case the precession will be clockwise as an observer from R side, so things will change. So instead when it is rising up, so I'll get the active will become reactive. So when it is rising up, we see that the bow is instead of rising straight, it will be rising towards the starboard side. So that will be the effect on the stability. Fine. So that is how we analyze the situation for the stability. So the third condition now is the rolling condition. So if we see the rolling condition, it is definitely never going to affect as such into the stability. So the third condition is called as the rolling condition. So for rolling, if I want to determine, so the gyroscopic couple during rolling will be I omega p, where again omega p is the precession velocity. So the precession velocity of rolling. But what happens in this rolling case is, we see that if this is the, so we have taken, or in this case the x-axis is the spin axis, right, and the rolling, so this is the spin axis, the rolling is also taking according to spin only. That means if I see, this is the spin vector, and we get that the precession vector to be parallel to the spin vector. So either it will be just along the spin vector, or it will be opposite to the spin vector, right? And how do we get the couple vector? When we rotate the spin vector in the direction of the couple vector. So that means it is not going to have as such any effect on the stability. So the rolling of the ship does not actually, theoretically I can find out, or I can just we can just say what is the magnitude of gyroscopic couple in such case, but it does not have any effect as such on the stability of the ship. So this is how the stability of the sea vessels or the ships are analyzed for the gyroscopic couple effect. So in this session what we have discussed, we have seen how the gyroscopic couple affects the stability of a ship basically in two conditions. One is the steering and the second is the pitching condition, and they do really affect the stability conditions, because the ship is a floating vessel which is on water, and the water does not give sufficient reaction for stability, right? So that means during such conditions the entire ship is having a tendency, not only tendency, rather we see the floating vessel is moving in the direction of the reaction, which may create problem for controlling the motion of such ships. So that is all in this session, and take care all.